Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we are going to take a deep dive into AWS Transit Gateway configuration using AWS command line interface commands. Transit Gateway is one of the most powerful networking services in AWS, acting as a central hub that connects multiple VPCs, VPN connections, and direct connect gateways together. Understanding how to configure it through the command line gives you precise control over your network architecture and enables automation through scripts and infrastructure as code. Transit Gateway solves a fundamental problem in AWS networking. Before Transit Gateway, if you wanted to connect multiple VPCs together, you would need to create individual VPC peering connections between each pair of VPCs. With just 5 VPCs, that would require 10 separate peering connections, and the complexity grows exponentially as you add more VPCs. Transit Gateway simplifies this by providing a single attachment point for each VPC, and the Transit Gateway handles routing between all connected networks. Looking at the diagram on this slide, you can see the Transit Gateway positioned at the center of the architecture. From the Transit Gateway, there are 4 arrows pointing outward to different types of connections. The first arrow points to VPC A, representing a spoke VPC attachment. The second arrow points to VPC B, another spoke VPC. The third arrow extends to the Direct Connect Gateway, which provides dedicated connectivity to on-premises data centers. The fourth arrow connects to the VPN connection, which provides encrypted connectivity over the public internet. This hub and spoke topology is the foundation of Transit Gateway architecture, where the Transit Gateway serves as the central routing hub and all other networks connect as spokes. Throughout this presentation, we will work through each type of attachment, configure route tables, set up routing between different network segments, and demonstrate the CLI commands needed at every step. Creating your Transit Gateway. The first step in building your Transit Gateway architecture is creating the Transit Gateway itself. This is accomplished using the Create Transit Gateway command, which offers several important configuration options that affect how your network will behave. Let me walk you through the command shown on this slide. The command begins with AWS EC2 Create Transit Gateway, which is the base command for creating a new Transit Gateway resource. The description parameter is set to Production Transit Gateway, which is simply a human-readable description that helps you identify the purpose of this Transit Gateway in the console and in API responses. The Options parameter is where the important configuration happens. The Amazon side ASN is set to 64512, which is the autonomous system number that AWS will use for BGP sessions. ASN 64512 falls within the private ASN range of 64512 to 65534, which is recommended for internal use. If you are connecting to on-premises networks that already use BGP, you need to ensure this ASN does not conflict with your existing ASN assignments. Auto Accept Shared Attachments is set to Enable, which means that when you share this Transit Gateway with other AWS accounts using Resource Access Manager, those accounts can create attachments without requiring manual approval. This is useful in organizations where you want to streamline the process of connecting new accounts. Default Route Table Association is set to Enable, which means that any new attachment created on this Transit Gateway will automatically be associated with the default route table. This simplifies initial setup, but you may want to disable this in more complex architectures where you need precise control over route table associations. Default route table propagation is also set to Enable, meaning that routes from attached networks will automatically propagate to the default route table. Combined with the previous setting, this creates an any-to-any connectivity model out of the box. VPN ECMP support is enabled, which allows equal-cost multipath routing for VPN connections. If you have multiple VPN tunnels to the same destination, traffic can be load balanced across them for increased throughput. Domain name system support is enabled, which allows domain name system resolution between connected VPCs. This is essential if your applications use private domain name system names to communicate with resources in other VPCs. The tag specifications parameter adds a name tag with the value prod TGW, making it easy to identify this transit gateway in the console and in CLI output. The command returns the transit gateway ID, which in our example is TGW-0ABC123DEF456789, and you will use this ID in subsequent commands to create attachments and configure routing. Looking at the diagram, you can see the transit gateway box at the center. From this central box, 4 configuration items branch out showing the key settings. The first branch shows ASN 64512, representing the BGP autonomous system number. The second branch shows auto accept enabled, indicating that shared attachments will be automatically accepted. The third branch shows default association enabled, meaning attachments auto associate with the default route table. The fourth branch shows DNS support enabled, allowing cross-VPC DNS resolution. This visual representation helps you understand that these settings are core properties of the transit gateway that affect all attachments and routing behavior. Attaching VPCs spokes to transit gateway. With the transit gateway created, the next step is attaching your VPCs. Each VPC attachment connects a VPC to the transit gateway, enabling traffic to flow between that VPC and other networks connected to the same transit gateway. The command shown uses AWS EC2 create transit gateway VPC attachment, which creates a new VPC attachment. The transit gateway ID parameter specifies TGW-0ABC beginning with 0A and ending with 89, which is the ID of the transit gateway we created in the previous step. You must reference the correct transit gateway ID to ensure the attachment is created on the right hub. The VPC ID parameter is set to VPC SPOCA-123456, which identifies the VPC you want to attach. This VPC must exist in the same region as the transit gateway, and you must have appropriate permissions to create attachments for this VPC. The subnet ID's parameter is critical and often misunderstood. When you attach a VPC to a transit gateway, AWS creates an elastic network interface in the specified subnets. These network interfaces are how traffic enters and exits the VPC through the transit gateway. In our command, we specify subnet 1A1 ending with 11 and subnet 1B2 ending with 22, placing network interfaces in 2 different availability zones. This provides high availability because if one availability zone experiences issues, traffic can still flow through the other subnet. The tag specifications parameter adds a name tag with the value SPOCA attachment, making it easy to identify this attachment. The command returns the attachment ID TGW-attach-spoke-a-001, which you will use when configuring route table associations and propagations. The second command block shows how to attach a second VPC, spoke B. The structure is identical but with different values. The VPC ID is VPC spoke B789012, and the subnet IDs are subnet 2A33333 and subnet 2B44444. This attachment gets the ID TGW attach spoke B002. By following this pattern, you can attach as many VPCs as needed, up to the transit gateway attachment limits. Now let me explain the diagram that visualizes this architecture. At the top center is the transit gateway box, representing our central hub. Below the transit gateway are 2 VPC boxes labeled VPC spoke A with CIDR 10.1.0.0/16 and VPC spoke B with CIDR 10.2.0.0/16. From the transit gateway, arrows point down to each VPC, and these arrows are labeled with the attachment IDs. The arrow to VPC spoke A is labeled TGW attach spoke A, and the arrow to VPC spoke B is labeled TGW attach spoke B. Within each VPC box, there are two smaller boxes representing subnets in different availability zones, showing where the transit gateway network interfaces are placed. This diagram illustrates how the transit gateway connects to multiple VPCs through separate attachments, with each attachment using subnets across availability zones for redundancy. Configuring Direct Connect Gateway Attachment. Connecting your transit gateway to a Direct Connect gateway enables hybrid connectivity between your AWS networks and on-premises data centers over dedicated, private network connections. This is essential for enterprises that require consistent network performance and cannot rely solely on internet-based VPN connections. Before we can attach a Direct Connect gateway to our transit gateway, we first need to create the Direct Connect gateway itself. The command AWS Direct Connect create Direct Connect gateway accomplishes this. The Direct Connect gateway name parameter is set to prod-dx-gateway, giving it an identifiable name. The Amazon side ASN parameter is set to 64513, which is the BGP ASN that AWS will use when establishing BGP sessions over Direct Connect. This ASN must be different from the Transit Gateway ASN we configured earlier, which was 64512, because they are separate BGP speakers. The command returns the Direct Connect Gateway ID, beginning with 0A and ending with 89. The second command creates the association between the Transit Gateway and the Direct Connect Gateway. The AWS Direct Connect create Direct Connect Gateway Association command links these two gateways together. The Direct Connect Gateway ID parameter references our newly created Direct Connect Gateway. The Gateway ID parameter references our Transit Gateway. The allowed prefixes parameter is crucial for security and routing control. It specifies which CIDR blocks can be advertised from AWS to your on-premises network through this association. In our example, we allow RFC 1918, which covers all our VPC address spaces, but you could restrict this to specific VPC CIDRs if you want more granular control. The diagram on this slide shows the complete Direct Connect connectivity path. At the far left is a box labeled On-Premises Data Center, representing your corporate network. From the data center, an arrow labeled Direct Connect points to a box labeled Direct Connect Location, which represents the physical colocation facility where AWS Direct Connect is available. From the Direct Connect location, another arrow points to the Direct Connect Gateway box. Finally, from the Direct Connect Gateway, an arrow points to the Transit Gateway. This chain shows how traffic flows from on-premises through the physical Direct Connect circuit to the Direct Connect location, through the Direct Connect Gateway which handles the BGP routing, and into the Transit Gateway which then routes to the appropriate VPCs. The diagram also shows the VPCs connected below the Transit Gateway, completing the picture of hybrid connectivity from on-premises to cloud resources. Setting up Site-to-Site VPN attachment. While Direct Connect provides dedicated connectivity, VPN connections offer a flexible and quick-to-deploy alternative that works over the public internet. Attaching a Site-to-Site VPN to your transit gateway enables encrypted connectivity to on-premises networks or even other cloud environments. The first command creates a customer gateway, which represents your on-premises VPN device in AWS. The AWS EC2 create customer gateway command requires several parameters. The type parameter is set to IPsec.1, which indicates this is an IPsec VPN device. This is currently the only supported type for site-to-site VPN. The public IP parameter is set to 203.0.113.100, which must be the public IP address of your on-premises VPN device. AWS will establish VPN tunnels to this IP address. The BGP ASN parameter is set to 65000, representing the BGP ASN of your on-premises network. This ASN will be used when establishing BGP sessions over the VPN tunnels. The command returns the customer gateway ID, CGW-0ABC123DEF456. The second command creates the VPN connection itself and attaches it directly to the transit gateway. The AWS EC2 create VPN connection command with type set to IPsec.1 creates an IPsec-based VPN. The customer gateway ID references the customer gateway we just created. The transit gateway ID references our transit gateway, which is the key parameter that makes this a transit gateway VPN attachment rather than a virtual private gateway VPN. The options parameter configures VPN-specific settings. Enable acceleration set to true enables AWS Global Accelerator for the VPN, which can improve performance by routing traffic through the AWS global network rather than the public internet. Tunnel inside IP version set to IPv4 specifies that the tunnel endpoints will use IPv4 addresses. The command returns the VPN connection ID VPN-0ABC123DEF456789. Looking at the diagram, at the left side is a box labeled Customer Site representing your on-premises location. Inside this box is a smaller box labeled Customer Gateway 203.0.1.1.3.100 showing the public IP of your VPN device. From the Customer Gateway, two arrows extend to the right, each labeled IPsec tunnel, representing the two VPN tunnels that AWS always creates for redundancy. These arrows connect to a box labeled VPN connection, which then connects via another arrow to the transit gateway on the right side. The transit gateway shows the VPN attachment ID. This diagram illustrates the redundant tunnel architecture where AWS provides two tunnels per VPN connection, terminating on different endpoints in the AWS infrastructure for high availability. Traffic from on-premises can use either tunnel, and if one fails, the other continues to carry traffic. Understanding Transit Gateway Route Tables. Route tables are the heart of transit gateway routing logic. They determine how traffic flows between the various attachments connected to your transit gateway. Understanding route tables is essential for building secure and efficient network architectures. Every transit gateway has at least one route table, which is the default route table created automatically. However, for more sophisticated routing requirements such as network segmentation or hub and spoke isolation, you will want to create additional route tables. The command AWS EC2 create transit gateway route table creates a new route table. The transit gateway ID parameter specifies which transit gateway this route table belongs to. The tag specifications parameter adds a name tag with the value production RT, making it easy to identify. The command returns the route table ID TGWRTB prod 001. The second command creates another route table named development RT with ID TGWRTB dev 002. By creating separate route tables, you can control which attachments can communicate with each other. There are two critical concepts to understand with route tables. First is association, which determines which route table an attachment uses for outbound traffic decisions. Each attachment can only be associated with one route table at a time. Second is propagation, which automatically adds routes from an attachment to a route table. An attachment can propagate its routes to multiple route tables, enabling other attachments associated with those tables to reach it. Looking at the diagram, the transit gateway is shown at the top center. Below it, two route table boxes branch off, one labeled production route table and one labeled development route table. From the production route table, arrows connect down to VPC boxes labeled prod VPCA and prod VPCB, showing that these production VPCs are associated with the production route table. From the development route table, arrows connect to boxes labeled dev VPCA and dev VPCB. A separate section shows the shared services VPC, which has arrows indicating it propagates routes to both route tables, meaning both production and development environments can reach shared services. This segmentation ensures that production VPCs only route traffic according to the production route table, and development VPCs use the development route table, providing network isolation while still allowing access to shared resources. Route table associations. Associating attachments with route tables is how you define which routing rules apply to traffic leaving each attachment. This is the mechanism that enables network segmentation and controlled traffic flow. Before creating new associations, you may need to remove existing associations, particularly if the attachment was automatically associated with the default route table when it was created. The command AWS EC2 disassociate Transit Gateway route table removes an existing association. The Transit Gateway route table ID specifies the route table currently associated, which is TGW-RTB-default in our example. The Transit Gateway attachment ID specifies the attachment TGW-attach-spoke-a-001 that we want to disassociate. After running this command, the attachment is no longer associated with any route table and will not be able to route traffic until you create a new association. The next command creates a new association with our production route table. The AWS EC2 Associate Transit Gateway Route Table command takes the Transit Gateway Route Table ID parameter set to TGW-RTB-prod-001, which is our production route table. The Transit Gateway Attachment ID is TGW-attach-spoke-a-001, the same attachment we just disassociated. After this command, any traffic leaving VPC spoke A through the Transit Gateway will be routed according to the rules in the production route table. The third command shows associating VPC spoke B with the development route table TGW-RTB-dev-002. This places spoke B under different routing rules than spoke A, even though they are both attached to the same transit gateway. This is how you achieve network segmentation. Looking at the diagram, it shows the before and after state of route table associations. On the left side labeled before, both VPC spoke A and VPC spoke B have arrows pointing to a single default route table box. On the right side labeled after, VPC spoke A has an arrow pointing to the production route table, while VPC spoke B has an arrow pointing to the development route table. The default route table is shown grayed out with no connections. This visual clearly demonstrates how changing associations moves attachments from shared routing to segmented routing, where each VPC now follows different routing rules based on its associated route table. Route propagation configuration. Route propagation is the mechanism that automatically populates route tables with the CIDR blocks of attached networks. This eliminates the need to manually create static routes for each attachment and automatically keeps routes updated as attachments are added or removed. The first command AWS EC2 enable Transit Gateway Route Table Propagation enables propagation from spoke A to the production route table. The Transit Gateway Route Table ID is TGW-RTB-prod-001, and the Transit Gateway Attachment ID is TGW-attach-spoke-a-001. After running this command, the CIDR block of VPC spoke A, which is 10.1.0.0/16, will automatically appear as a route in the production route table with a next hop of the spoke A attachment. The second command enables propagation from spoke B to the development route table TGW-RTB-dev-002. This adds the 10.2.0.0/16 CIDR to the development route table. The third command demonstrates cross-propagation, which is key to enabling connectivity between network segments. Here we enable propagation from shared services attached to both the production route table in this command and the development route table in the fourth command. This means the shared services CIDR will appear in both route tables, allowing both production and development VPCs to reach shared services. The fifth command shows the reverse propagation, enabling the production attachment to propagate to the shared services route table. This ensures bidirectional connectivity where shared services can also read production resources. Looking at the diagram, it illustrates the propagation relationships using a network graph style. At the center is the transit gateway. 3 route table boxes surround it representing production RT, development RT, and shared services RT. Arrows with labels show propagation flows. An arrow from VPC spoke points into production RT labeled propagates 10.1.0.0/16. An arrow from VPC spoke B points into development RT labeled propagates 10.2.0.0/16. From the shared services VPC, arrows extend to both production RT and development RT, both labeled propagates 10.3.0.0/16. Reverse arrows from production and development VPCs point into shared services RT, showing bidirectional propagation. This creates a routing topology where production and development networks are isolated from each other but both can communicate with shared services. Creating static routes. While route propagation handles dynamic route population for VPC attachments, static routes are necessary for certain scenarios, particularly for directing traffic to VPN or direct connect attachments, creating default routes, or implementing more specific routing policies. The first command creates a static route in the production route table directing all traffic destined for RFC 1918 to the VPN attachment. The AWS EC2 Create Transit Gateway Route command takes the Transit Gateway Route Table ID parameter set to TGW-RTB-prod-001. The destination CIDR block is RFC 1918, which represents your on-premises network address space. The Transit Gateway Attachment ID is VPN-attach-001, pointing to the VPN attachment. After this command, any traffic in the production route table destined for RFC 1918 will be sent through the VPN tunnel. The second command creates a similar route to the on-premises network but through the Direct Connect attachment DXGW-attach-001. You might have this configured as a backup route or for a different on-premises site. The third command creates a default route, shown by destination CIDR block quad 0/0. This catches all traffic that does not match any more specific route and sends it to the egress VPC attachment. This pattern is commonly used in centralized egress architectures where all internet-bound traffic is funneled through a dedicated egress VPC containing NAT gateways or firewall appliances. The fourth command demonstrates creating a blackhole route. By adding the blackhole parameter instead of an attachment ID, the route will drop all traffic matching 10.99.0.0/16. Blackhole routes are useful for security purposes, such as ensuring traffic to a decommissioned network is explicitly dropped rather than potentially misrouted. Looking at the diagram, it shows a routing decision tree. At the top is an incoming traffic box. From this, arrows branch down to different routes. The first arrow labeled 192.168.0.0/16 leads to a VPN gateway box. The second arrow labeled 172.16.0.0/12 leads to a direct connect gateway box. The third arrow labeled quad 0/0 default leads to an egress VPC box. The fourth arrow labeled 10.99.0.0/16 leads to a blackhole box shown in red. Each path illustrates how static routes direct traffic to different destinations based on the destination CIDR, with the default route catching everything else and the blackhole explicitly dropping specific traffic. Viewing and verifying routes. After configuring your transit gateway with attachments, associations, propagations, and static routes, it is essential to verify that the routing tables contain the expected entries. The Search Transit Gateway Routes command allows you to query and inspect routes in any Transit Gateway route table. The first command, AWS EC2 Search Transit Gateway Routes, queries the production route table. The Transit Gateway Route Table ID parameter specifies TGW-RTB-prod-001. The filters parameter uses the name state with a value of active to only return routes that are currently active and usable. The output table parameter formats the results as a table for easy reading. This command will display all active routes, including both propagated routes from VPC attachments and any static routes you created. The output shown on the slide displays 4 routes. The first route shows CIDR 10.1.0.0/16 with type propagated, attachment ID TGW-attach-spoke-A, and state active. This route was automatically created when we enabled propagation from spoke A. The second route shows 10.3.0.0/16 with type propagated from the shared services attachment. The third route shows 192.168.0.0/16 with type static going to the VPN attachment, which is the static route we created for on-premises connectivity. The fourth route shows quad 0/0 with type static pointing to the egress VPC attachment, which is our default route for internet-bound traffic. The second command uses the describe transit gateway route tables command to get detailed information about the route table itself, including association and propagation counts. The filter uses the transit gateway route table ID to target our production table specifically. Looking at the diagram, it presents the route table as a visual table structure. The table header shows production route table ID TGW-RTB-prod-001. Below are 4 rows representing each route. The first row shows a VPC icon next to 10.1.0.0/16 pointing to spoke A attachment with a green propagated badge. The second row shows another VPC icon next to 10.3.0.0/16 pointing to shared services with a green propagated badge. The third row shows a VPN icon next to 192.168.0.0/16 pointing to VPN attachment with a blue static badge. The fourth row shows a globe icon next to quad 0/0 pointing to egress VPC with a blue static badge. This visual representation makes it easy to understand at a glance what routes exist, their types, and where traffic will be directed for each destination. Also, hit the bell icon. After configuring your transit gateway with attachments and route tables, you must also configure the route tables within each VPC to direct traffic toward the transit gateway. This is a critical step that is often overlooked. Without proper VPC route table configuration, instances in your VPCs will not know to send traffic through the transit gateway attachment. The first command creates a route in a VPC route table directing traffic destined for another VPC through the transit gateway. The AWS EC2 create route command takes the route table ID parameter set to RTB spoke A private, which is the route table ID for the private subnets in spoke A. The destination CIDR block is 10.2.0.0/16, which is the CIDR of VPC spoke B that we want to read. The transit gateway ID is TGW0ABC1. 23DEF4567889, which tells AWS to send matching traffic to the transit gateway attachment in this VPC. The second command adds a route for the on-premises network 192.168.0.0/16. Any traffic from instances in spoke A destined for on-premises addresses will be sent to the transit gateway, which will then route it through either the VPN or direct connect attachment based on its route table configuration. The third command creates a default route quad 0/0 pointing to the transit gateway. This is used in centralized egress architectures where all internet-bound traffic from spoke VPCs is routed through a central egress VP circuit. Instead of each VPC having its own NAT gateway, traffic flows to the transit gateway and then to a dedicated egress VPC. The fourth command shows how to read the current routes in a VPC route table using the describe route tables command. The filters parameter targets a specific route table by ID. The query parameter extracts just the routes from the output, and the output table formats it for easy reading. Looking at the diagram, it shows the traffic flow from an EC2 instance through the VPC route table to the transit gateway. At the left is a box labeled EC2 instance representing a workload in VPC spoke A. An arrow from the instance points to a box labeled VPC route table, which contains 3 route entries shown as smaller boxes inside. The first entry shows 10.2.0.0/16 pointing to TGW. The second shows 192.168.0.0/16 pointing to TGW. And the third shows quad 0/0 pointing to TGW. From the VPC route table, a large arrow points to the transit gateway box on the right. From the transit gateway, 3 arrows branch out to different destinations corresponding to each route. This illustrates how the VPC route table is the first routing decision point, and it must be configured to send cross-VPC and external traffic to the transit gateway. Transit gateway peering across regions. Transit gateway peering allows you to connect transit gateways in different AWS regions, enabling you to build global networks that span multiple geographic locations. This is essential for enterprises with workloads distributed across regions for latency, compliance, or disaster recovery requirements. The first command creates a transit gateway peering attachment request from the requester region. The AWS EC2 create transit gateway peering attachment command initiates the peering connection. The transit gateway ID parameter specifies your local transit gateway TGW US East 1001 in the requester region. The peer transit gateway ID parameter specifies the transit gateway TGW EU West 1001 in the remote region that you want to peer with. The peer account ID is the AWS account ID account number that owns the peer transit gateway. This can be the same account for intra-organization peering or a different account for cross-account peering. The peer region parameter specifies EU West 1 as the AWS region where the peer transit gateway resides. The command returns the peering attachment ID TGW attach peer 001. The second command accepts the peering request from the acceptor region. You must run this command in the peer region EU West 1 where the target transit gateway exists. The AWS EC2 accept transit gateway peering attachment command takes the transit gateway attachment ID parameter with the peering attachment ID returned from the first command. After acceptance, the peering attachment state changes from pending acceptance to available. The third command creates a static route in the US East Transit Gateway route table to direct traffic destined for the EU VPCs through the peering attachment. The destination CIDR block is 10.100.0.0/16, representing the CIDR range of VPCs attached to the EU Transit Gateway. The Transit Gateway attachment ID points to the peering attachment. Unlike VPC attachments, peering attachments do not support route propagation, so you must create static routes manually for all CIDRs you want to reach across the peering connection. The fourth command creates the corresponding return route in the EU West Transit Gateway, directing traffic for 10.0.0.0/16 representing US VPCs back through the same peering attachment. Looking at the diagram, it shows 2 regions side by side. On the left is a box labeled US East 1 region containing a transit gateway labeled TGW US East with 2 VPC boxes below it. On the right is a box labeled EU West 1 region containing another transit gateway labeled TGW EU West with 2 VPC boxes below it. Between the 2 transit gateways is a bidirectional arrow labeled peering attachment with the ID shown. Below each transit gateway, route table boxes show the static routes. The US route table shows 10.100.0.0/16 pointing to peering, and the EU route table shows 10.0.0.0/16 pointing to peering. This diagram illustrates how peering creates a direct connection between transit gateways, with static routes enabling traffic to flow between regions. Transit Gateway Connect attachments for SD-WAN. Transit Gateway Connect is a feature that enables you to integrate third-party SD-WAN appliances with your transit gateway using the GRE protocol and BGP for dynamic routing. This is particularly useful when you have existing SD-WAN infrastructure and want to extend it into AWS. The first command creates a Transit Gateway Connect attachment. The AWS EC2 Create Transit Gateway Connect command requires the Transport Transit Gateway Attachment ID parameter, which specifies an existing VPC attachment, TGW-attach-SD-WAN-VPC, that will serve as the transport layer for the Connect attachment. The Connect attachment uses this underlying VPC attachment to carry the GRE tunnels. The option parameter includes protocol set to GRE, which is currently the only supported encapsulation protocol. The command returns the Connect attachment ID, TGW-attach-connect-001. The second command creates a Connect peer, which represents the actual GRE tunnel endpoint to your SD-WAN appliance. The AWS EC2 Create Transit Gateway Connect Peer command takes the Transit Gateway Attachment ID of the Connect attachment we just created. The peer address parameter is 10.0.1.100, which is the private IP address of your SD-WAN appliance inside the Transport VPC. The Transit Gateway address parameter is 10.0.1.200, which is the IP address that the Transit Gateway will use as its tunnel endpoint. The Inside CIDR blocks parameter specifies 169.254.100.0/29, which defines the IP addresses used inside the GRE tunnel for BGP peering. This CIDR provides addresses for both the Transit Gateway and the Connect peer to establish BGP sessions. The BGP options parameter sets peer ASN to 65001, which is the BGP ASN of your SD-WAN appliance. The third command describes the Connect peer to verify its configuration and check the BGP session status. The filters parameter targets our specific Connect peer by ID. Enabling Transit Gateway Multicast. Transit Gateway Multicast enables you to distribute traffic to multiple destinations simultaneously using multicast protocols. This is valuable for applications like video streaming, financial market data distribution, or any scenario where the same data needs to read multiple receivers efficiently. Before using multicast, you must ensure your transit gateway was created with multicast support enabled. If not, you need to create a new transit gateway with the multicast support option set to enable. The first command shows creating a multicast-enabled transit gateway using AWS EC2 Create Transit Gateway with the options parameter including multicast support set to enable. The second command creates a transit gateway multicast domain, which is a logical grouping for multicast traffic. The AWS EC2 Create Transit Gateway Multicast Domain command takes the Transit Gateway ID parameter pointing to our multicast-enabled transit gateway. The options parameter includes IGMPv2 support set to enable, which allows members to join and leave multicast groups dynamically using IGMP version 2 protocol. Static sources support is set to enable, allowing you to define static multicast sources. Auto-accept shared associations is set to enable for cross-account scenarios. The command returns the multicast domain ID, TGW-mcast-domain-001. The third command associates a VPC subnet with the multicast domain. The AWS EC2 Associate Transit Gateway Multicast Domain command links a specific subnet to the multicast domain. The Transit Gateway Multicast Domain ID specifies our domain. The Transit Gateway Attachment ID is the VPC attachment containing the subnet. The subnet ID's parameter specifies the subnet multicast 001 where multicast sources or receivers reside. The fourth command registers a multicast group source. The AWS EC2 registered Transit Gateway Multicast Group Sources command defines which network interface can send traffic to a multicast group. The group IP address is 239.1.1.1, which is a multicast IP address in the organizationally scoped range. The network interface ID's parameter specifies the ENI any source 001 of the instance that will be the multicast source. The fifth command registers multicast group members, which are the receivers. The AWS EC2 registered Transit Gateway Multicast Group Members command registers ENIs that will receive multicast traffic for the group IP address. Network segmentation with multiple route tables. Implementing network segmentation using multiple Transit Gateway route tables is a powerful pattern for isolating different environments or business units while still allowing controlled connectivity to shared resources. Let me walk you through a complete segmentation setup. The first set of commands creates 3 separate route tables for production, development, and shared services. Each AWS EC2 Create Transit Gateway Route Table command creates a route table with a descriptive name tag. The production route table gets ID TGW-RTB-prod, development gets TGW-RTB-dev, and shared services gets TGW-RTB-shared. The second set of commands associates VPC attachments with their respective route tables. Production VPCs are associated with the production route table, development VPCs with the development route table, and the shared services VPC with the shared services route table. Each association uses the AWS EC2 Associate Transit Gateway Route Table command with the appropriate route table ID and attachment ID. The third set of commands configures propagation to enable connectivity. For the production route table, we enable propagation from all production VPCs and from shared services, but critically not from development. This means production can reach other production VPCs and shared services, but cannot reach development. Similarly, for the development route table, we enable propagation from development VPCs and shared services, but not from production. For the shared services route table, we enable propagation from both production and development VPCs so that shared services can respond to requests from either environment. Looking at the diagram, it shows the segmentation architecture. At the center is the transit gateway. 3 route table boxes branch from it labeled production RT, development RT, and shared services RT. Below production RT, 2 VPC boxes labeled Prod VPCA and Prod VPCB connect with solid arrows indicating association. Below development RT, 2 VPC boxes labeled Dev VPCA and Dev VPCB connect similarly. At the bottom center, a shared services VPC box has dashed arrows extending to both production RT and development RT, indicating it propagates routes to both. A red X mark between production RT and development RT visually indicates that there is no route propagation between these tables, enforcing isolation. The shared services VPC is positioned to show it can be reached from both environments while production and development cannot reach each other directly. Appliance Mode for stateful inspection. When routing traffic through security appliances like firewalls or IDS/IPS in a transit gateway architecture, you need to enable Appliance Mode on the VPC attachment. This ensures that traffic flows symmetrically through the same appliance for both directions of a connection, which is essential for stateful inspection. Without Appliance Mode, the transit gateway uses ECMP equal cost multipath routing to distribute traffic across availability zones. This can cause asymmetric routing where the request goes through one firewall instance and the response returns through a different instance. Since stateful firewalls maintain connection state tables, asymmetric routing breaks the firewall's ability to track and inspect connections properly. The first command modifies an existing VPC attachment to enable appliance mode. The AWS EC2 modified Transit Gateway VPC attachment command takes the Transit Gateway attachment ID of the security VPC attachment. The option parameter includes appliance mode support set to enable. After running this command, the Transit Gateway will ensure that return traffic for a flow uses the same availability zone as the original traffic, maintaining symmetry through the firewall appliances. The second command shows how to create a new VPC attachment with appliance mode enabled from the start. The AWS EC2 Create Transit Gateway VPC attachment command includes the options parameter with appliance mode support set to enable. This is the preferred approach when deploying new security VPCs. The third command verifies the appliance mode setting by describing the attachment. The query parameter extracts just the options section to confirm appliance mode support shows enable. Looking at the diagram, it contrasts the traffic flow with and without appliance mode. On the left side labeled without appliance mode, traffic from source VPC goes through the Transit Gateway, which distributes it across two firewall boxes in different availability zones. The arrows show request going through Firewall Availability Zone 1 and response coming back through Firewall Availability Zone 2, with a warning symbol indicating asymmetric routing. On the right side labeled with Appliance Mode, the same source traffic goes through the Transit Gateway, but now both request and response arrows go through the same Firewall Availability Zone 1, with a checkmark indicating symmetric routing. This visual clearly demonstrates why appliance mode is critical for stateful security appliances. Sharing Transit Gateway across accounts. AWS Resource Access Manager allows you to share your Transit Gateway with other AWS accounts in your organization, enabling a centralized networking model where a network team manages the Transit Gateway while application teams in other accounts can attach their VPCs. The first command creates a Resource Access Manager resource share. The AWS RAM Create Resource Share command takes the name parameter set to Transit Gateway Share for identification. The Resource ARNs parameter specifies the ARN of the Transit Gateway you want to share, following the format ARN:AWS:EC2:region:account number:transit gateway/TGWID. The principals parameter specifies who can access this share. You can share with specific account IDs, organizational unit ARNs, or the entire organization ARN as shown with ARN:123456789012:organization/organization/o example. The second command shows how a recipient account attaches a VPC to the shared Transit Gateway. From the recipient account, you run the standard AWS EC2 Create Transit Gateway VPC attachment command, but you specify the Transit Gateway ID of the shared Transit Gateway. The attachment will be created in the pending acceptance state unless the Transit Gateway was configured with Auto Accept Shared Attachments enabled. The third command, run from the Transit Gateway owner account, accepts the attachment request. The AWS EC2 Accept Transit Gateway VPC attachment command takes the Transit Gateway attachment ID of the pending attachment. After acceptance, the attachment becomes available and can be used for routing. The fourth command demonstrates listing all attachments on the Transit Gateway including those from other accounts. The AWS EC2 Describe Transit Gateway Attachments command filtered by Transit Gateway ID shows attachments from all accounts that have attached to this Transit Gateway. Look, prefix list references in route tables. Managing routes in Transit Gateway route tables can become complex when you have many destinations, especially for on-premises networks that may have numerous CIDR blocks. Prefix list references allow you to group multiple CIDRs into a managed prefix list and reference that list in your route table, simplifying management and ensuring consistency. The first command creates a managed prefix list. The AWS EC2 create managed prefix list command takes the prefix list name parameter set to on-prem networks for identification. The max entries parameter is set to 20, defining the maximum number of CIDR entries this list can contain. You should set this to accommodate your current needs plus future growth, as increasing it later requires creating a new version. The address family parameter is IPv4, specifying this list contains IPv4 CIDRs. The entries parameter contains the initial list of CIDRs, in this case 192.168.0.0/16 and 172.16.0.0/12, representing on-premises network ranges. The command returns the prefix list IDPL on-prem 001. The second command creates a prefix list reference in the Transit Gateway route table. The AWS EC2 create Transit Gateway prefix list reference command takes the Transit Gateway route table ID of the route table where you want to add the reference. The prefix list ID specifies the managed prefix list we created. The Transit Gateway attachment ID points to the attachment where traffic matching any CIDR in the prefix list should be sent. In this case, the VPN attachment. This single command effectively creates routes for all CIDRs in the prefix list. The third command shows how to add new entries to the prefix list using modify managed prefix list. The current version parameter ensures you are modifying the expected version of the list, preventing concurrent modification issues. The add entries parameter adds a new CIDR 10.100.0.0/16 to the list. When you add entries to the prefix list, the Transit Gateway route table automatically includes routes for the new CIDRs without requiring additional route table commands. The fourth command verifies the prefix list reference in the route table using get Transit Gateway prefix list references. Monitoring Transit Gateway with CloudWatch. Monitoring your Transit Gateway is essential for understanding traffic patterns, identifying issues, and capacity planning. AWS CloudWatch provides metrics for Transit Gateway attachments that you can query, visualize, and alarm on. The first command retrieves the bytes in metric for a specific attachment. The AWS CloudWatch get metric statistics command takes several parameters. The namespace parameter is AWS/Transit Gateway, which is where all Transit Gateway metrics are published. The metric name is bytes in, representing the number of bytes received by the attachment. The dimensions parameter specifies which attachment to query using the Transit Gateway attachment dimension with our attachment ID. The start time and end time parameters define the query window, in this case the last hour. The period parameter is 300, meaning the data will be aggregated into 5-minute intervals. The statistics parameter requests the sum statistic, giving total bytes for each period. The second command queries the packets in metric, which counts the number of packets rather than bytes. This is useful for understanding packet rates and detecting unusual patterns. The third command creates a CloudWatch alarm that triggers when bytes exceed a threshold. The AWS CloudWatch put metric alarm command takes the alarm name parameter for ID. The metric name is bytes in and namespace is AWS/Transit Gateway. The dimensions target our specific attachment. The statistic is sum and period is 300 seconds. The threshold is set to 1 billion, which is 1 gigabyte. The comparison operator is greater than threshold, meaning the alarm triggers when traffic exceeds 1 gigabyte in a 5-minute period. The evaluation periods parameter is 2, requiring 2 consecutive periods above threshold before alarming to avoid false positives from brief spikes. The alarm actions parameter specifies an SNS topic ARN where notifications will be sent when the alarm triggers. The fourth command lists all available metrics for Transit Gateway, helping you discover what metrics are available for monitoring. Troubleshooting Transit Gateway connectivity. When connectivity issues arise in your Transit Gateway architecture, systematic troubleshooting using CLI commands helps identify the root cause quickly. Let me walk you through the essential diagnostic commands. The first command checks the attachment state using describe transit gateway attachments. The filters parameter targets a specific attachment by ID. The query extracts the state field, and the output text format gives a clean single-value response. A healthy attachment shows available state. If you see pending, pending acceptance, or failed, the attachment is not ready for traffic. The second command searches for routes to verify the routing configuration. The AWS EC2 Search Transit Gateway Routes command queries the route table for a specific destination CIDR. The filters parameter uses route search.exact match with the destination CIDR you are trying to reach. If this returns no results, there is no route for that destination in the route table, which explains the connectivity failure. The third command checks the VPC route table to ensure traffic is being sent to the transit gateway in the first place. The AWS EC2 Describe Route Tables command filtered by the VPC route table ID shows all routes. Look for routes pointing to the transit gateway ID for the destinations you need to reach. The fourth command verifies security group rules on the EC2 instances. Even if routing is correct, security groups may be blocking the traffic. The AWS EC2 Describe Security Groups command shows inbound and outbound rules for a specific security group. The fifth command checks network access control rules on the subnets. NATs are stateless and require both inbound and outbound rules for traffic to flow. The sixth command uses VPC Reachability Analyzer to automate path analysis. The AWS EC2 Create Network Insights Path command defines a path from a source ENI to a destination ENI with protocol TCP and port 443. The AWS EC2 Start Network Insights Analysis command then analyzes this path and identifies where connectivity is blocked. Looking at the diagram, it shows a troubleshooting decision tree. At the top is a box labeled Connectivity Issue. From this, the first decision diamond asks attachment state available with yes and no branches. The no branch leads to check attachment status. The yes branch continues to another diamond asking route exists in TGWRT with branches leading to add missing route or continuing. The next diamond asks VPC route to TGW which leads to update VPC route table or continues. Then security group allows leads to update SG rules or continues. Finally NAT allows leads to update NAT rules or a green success box. Each decision point corresponds to one of the command line interface commands discussed, showing the systematic approach to isolating connectivity issues. Transit Gateway Flow Logs capture information about IP traffic flowing through your transit gateway, providing visibility into network communications for security analysis, troubleshooting, and compliance requirements. Unlike VPC flow logs which capture traffic at the network interface level, Transit Gateway flow logs capture traffic as it passes through the transit gateway itself. The first command creates a CloudWatch logs log group to store the flow logs. The AWS Logs Create Log Group command takes the log group name parameter set to /AWS/Transit Gateway/TGW flow logs. This log group will receive all the flow log records. You can configure retention periods and access controls on this log group separately. The second command creates the flow log itself. The AWS EC2 Create Flow Logs command requires several parameters. The resource type parameter is set to Transit Gateway, indicating we are creating flow logs for a transit gateway rather than a VPC or network interface. The resource IDs parameter specifies the transit gateway ID TGW-0ABC123DEF456789. The traffic type parameter is set to all, which captures both accepted and rejected traffic. You could also specify accept or reject to capture only specific traffic types. The log destination type is CloudWatch logs, directing the logs to CloudWatch. Alternatively, you could use S3 to send logs to an S3 bucket. The log destination parameter specifies the ARN of our CloudWatch log group. The max aggregation interval parameter is set to 60 seconds, meaning flow records are aggregated and published every minute. You can also set this to 600 for 10-minute intervals, which reduces costs but provides less granular data. The log format parameter customizes which fields are included in the flow records. The third command queries the flow logs using CloudWatch Logs Insights. The AWS Logs Start Query command runs an analytical query against the logs. The query counts traffic by source and destination VPC pairs, showing the top talkers in your transit gateway network. Looking at the diagram, it shows the flow log data pipeline. At the left, the transit gateway box has multiple attachment connections represented by lines to VPC boxes. From the transit gateway, a dashed arrow labeled flow log data points to a CloudWatch Logs box. Inside CloudWatch Logs, a log group icon is shown with sample log entries. From CloudWatch Logs, two arrows emerge. One points to a CloudWatch Insights box representing query and analysis capabilities. The other points to an S3 bucket box for long-term archival, transit gateway cost analysis and optimization. Understanding transit gateway costs is essential for optimizing your network expenses. Transit gateway pricing has two components: an hourly attachment charge and a data processing charge per gigabyte. Let me show you how to analyze and optimize these costs using CLI commands. The first command uses AWS Cost Explorer to retrieve transit gateway costs, broken down by usage type. The AWS CE Get Cost and Usage command takes the time period parameter with start and end dates, defining the analysis window. The granularity parameter is monthly for aggregated monthly data. The metrics parameter requests unblended cost, which shows the actual charges. The filter parameter limits results to the EC2 service and usage types containing transit gateway. The group by parameter groups results by usage_type, allowing you to see attachment hours versus data processing charges separately. The second command retrieves CloudWatch metrics to understand data transfer volumes per attachment. The AWS CloudWatch Get Metric Statistics command queries bytes in and bytes out metrics for a specific attachment over the past month. By summing these values, you can calculate total data processed and estimate the data processing charges. The third command lists all attachments with their types, helping you identify which attachments exist and potentially which ones can be consolidated or removed. The AWS EC2 Describe Transit Gateway Attachments command, filtered by the Transit Gateway ID, returns all attachments with their resource types and states. Equal cost multipath and VPN bandwidth aggregation. Equal cost multipath routing allows you to aggregate bandwidth across multiple VPN tunnels by distributing traffic across them. When you enable ECMP on your transit gateway, traffic to the same destination can be load balanced across multiple equal cost paths, effectively increasing your available bandwidth beyond a single tunnel's limit. The first command verifies that equal cost multipath routing is enabled on your transit gateway. The AWS EC2 Describe Transit Gateways command, filtered by your Transit Gateway ID, extracts the options section which shows VPN equal cost multipath support status. If this shows disable, you need to enable it when creating a new transit gateway, as this option cannot be changed after creation. The second command creates multiple VPN connections to the same customer gateway. By creating two VPN connections to the same on-premises device, you effectively get 4 tunnels, since each VPN connection provides 2 tunnels for redundancy. The AWS EC2 Create VPN Connection command is run twice with the same customer gateway ID but creates separate VPN connections. Each connection is tagged distinctly as VPN ECMP1 and VPN ECMP2 for identification. The third command verifies that BGP is establishing sessions across all tunnels. The AWS EC2 Describe VPN Connections command with a query for the VGW telemetry section shows the status of each tunnel, including the BGP status and the number of routes being advertised. For equal cost multipath routing to work correctly, all VPN tunnels must advertise the same routes with the same BGP attributes. The transit gateway will then distribute traffic across all available paths using a 5-tuple hash of source IP, destination IP, source port, destination port, and protocol. This means that individual flows stay on the same path for consistency, but different flows are distributed across tunnels. IPv6 support and dual stack configuration. Transit Gateway supports IP version 6 addressing, allowing you to build dual stack networks that can route both IP version 4 and IP version 6 traffic. This is increasingly important as organizations adopt IP version 6 for new workloads and prepare for IP version 4 address exhaustion. The first command creates a VPC with both IP version 4 and IP version 6 CIDR blocks. The AWS EC2 create VPC command uses the CIDR block parameter for the IP version 4 range 10.1.0.0/16. The Amazon provided IP version 6 CIDR block parameter set to true requests AWS to assign an IP version 6 CIDR block from Amazon's pool. This creates a dual-stack VPC that can host resources with both IP version 4 and IP version 6 addresses. The second command associates an IP version 6 CIDR block with an existing VPC if it was created without one. The AWS EC2 Associate VPC CIDR block command with Amazon provided IP version 6 CIDR block adds IP version 6 capability to a VPC that initially only had IP version 4. The third command creates a subnet with both IP version 4 and IP version 6 addressing. The CIDR block parameter provides the IP version 4 subnet range 10.1.1.0/24. The IP version 6 CIDR block parameter specifies the IP version 6 range using the format that appends a subnet identifier to the VPC's IP version 6 CIDR. The double colon followed by 01 and the /64 prefix length creates a unique IP version 6 subnet within the VPC's allocation. The fourth command creates a transit gateway VPC attachment that supports IPv6. When attaching a dual-stack VPC, the attachment automatically supports both protocols. The options parameter with IPv6 support set to enable ensures IPv6 routing is active for this attachment. The fifth command creates an IP version 6 route in the transit gateway route table. The AWS EC2 Create Transit Gateway Route command uses an IP version 6 destination CIDR block in the format 2600:1F18:example::/48. Note that IP version 6 routes are managed separately from IP version 4 routes in the same route table. Transit Gateway Policy Tables. Transit Gateway Policy Tables provide an additional layer of routing control specifically designed for inter-region peering scenarios. While regular route tables determine where to send traffic based on destination, policy tables can influence routing decisions based on the source of traffic, enabling more sophisticated routing policies. The first command creates a Transit Gateway Policy Table. The AWS EC2 Create Transit Gateway Policy Table command takes the Transit Gateway ID parameter specifying which transit gateway owns this policy table. The tag specifications parameter adds a descriptive name inter-region policy for identification. The command returns the policy table ID TGW-PTB-001. The second command associates the policy table with a peering attachment. The AWS EC2 Associate Transit Gateway Policy Table command links the policy table to the peering attachment. Only peering attachments can be associated with policy tables. The combination of Transit Gateway Policy Table ID and Transit Gateway Attachment ID creates the association. The third command creates a policy table entry that defines the routing policy. The AWS EC2 Create Transit Gateway Policy Table entry command is complex and requires careful attention to parameters. The Transit Gateway Policy Table ID specifies our policy table. The source CIDR block parameter is 10.1.0.0/16, defining which source addresses this policy applies to. The destination CIDR block is 10.100.0.0/16, the destination network. The Transit Gateway Attachment ID specifies where matching traffic should be sent, in this case the peering attachment. The metadata parameter includes association with a Transit Gateway route table ID, linking this policy entry to a specific route table for further routing decisions. The fourth command retrieves policy table entries to verify the configuration. The AWS EC2 Get Transit Gateway Policy Table Entries command filtered by the policy table ID returns all entries with their source and destination CIDRs and target attachments. Migrating from VPC peering to Transit Gateway. Many organizations start with VPC peering for simple connectivity requirements but find they need to migrate to Transit Gateway as their networks grow. This migration requires careful planning to avoid connectivity disruptions. Let me walk through a migration strategy using CLI commands. The first step is documenting your existing VPC peering connections. The AWS EC2 Describe VPC Peering Connections command retrieves all peering connections. The query extracts the VPC peering connection ID, the requester and acceptor VPC IDs and CIDRs, and the current status. This gives you a complete inventory of what needs to be migrated. The second command creates the Transit Gateway and the necessary VPC attachments as we covered in earlier slides. For migration, you want to create all attachments and configure route tables before switching traffic. The third step involves adding Transit Gateway routes to your VPC route tables alongside the existing peering routes. The AWS EC2 Create Route command adds a route for a destination CIDR through the Transit Gateway. At this point, both routes exist but the more specific route wins. If your peering route and Transit Gateway route have the same specificity, AWS uses the route that was created first. The fourth command implements the cutover by replacing the peering route with the Transit Gateway route. The AWS EC2 Replace Route command atomically updates the route from the peering connection to the Transit Gateway. This is the moment when traffic shifts from VPC peering to Transit Gateway. You should execute this during a maintenance window and verify connectivity immediately after. The fifth command deletes the VPC peering connection after successful migration. The AWS EC2 Delete VPC Peering Connection command removes the peering connection identified by its ID. Only execute this after confirming all traffic is flowing correctly through Transit Gateway. Transit Gateway with AWS Network Firewall. Integrating AWS Network Firewall with Transit Gateway creates a centralized inspection architecture where all traffic between VPCs or between VPCs and external networks passes through the firewall for deep packet inspection, intrusion detection, and policy enforcement. The first command creates the network firewall in a dedicated inspection VPC. The AWS Network Firewall Create Firewall command takes the firewall name parameter for identification. The firewall policy ARN specifies the ARN of a firewall policy you have previously created that defines the inspection rules. The VPC ID is the inspection VPC where the firewall will be deployed. The subnet mappings parameter specifies subnets in each availability zone where firewall endpoints will be created. The command returns the firewall ARN and the sync states showing endpoint creation progress. The second command describes the firewall to read the endpoint IDs. The AWS Network Firewall Describe Firewall command returns detailed information including the firewall endpoint IDs in each availability zone. These endpoint IDs are needed for routing configuration. The third command creates routes in the inspection VPC to direct traffic through the firewall endpoints. Traffic arriving from the Transit Gateway attachment subnet must be routed to the firewall endpoint. The AWS EC2 create route command creates a route for the spoke VPC CIDR 10.1.0.0/16 pointing to the firewall endpoint VPC-EE-FW-AZ1. The fourth command creates the return route from the firewall subnet to the transit gateway. After inspection, traffic destined for other networks must be sent back to the transit gateway for final routing. The route uses destination quad 0/0 pointing to the transit gateway ID. The fifth command configures the transit gateway route table to send spoke VPC traffic through the inspection VPC. A default route quad 0/0 in the spoke route table points to the inspection VPC attachment, ensuring all inter-VPC traffic passes through the firewall. Automating transit gateway with CloudFormation. While CLI commands are excellent for understanding and ad hoc operations, production transit gateway deployments should be managed as infrastructure as a service using CloudFormation or Terraform. This ensures consistency, enables version control, and facilitates disaster recovery. The first command deploys a CloudFormation stack that creates a transit gateway with all its components. The AWS CloudFormation create stack command takes the stack name parameter for identification. The template body parameter specifies the path to your CloudFormation template file. The parameter passes values to the template such as the environment name and ASN. The capabilities parameter with capability IAM acknowledges that the template may create IAM resources. The second command shows the structure of a CloudFormation template for Transit Gateway. The template creates the Transit Gateway resource with all the options we have discussed, including Amazon Side ASN, auto-accept shared attachments, default route table association, default route table propagation, DNS support, and VPN eCMP support. Each property maps directly to the CLI options we used in the Create Transit Gateway command. The third command shows how to create VPC attachments using CloudFormation intrinsic functions. The Transit Gateway ID uses the ref function to reference the transit gateway created in the same template. The VPC ID and subnet IDs can use parameters or references to other resources in the template. The fourth command demonstrates using CloudFormation stack sets to deploy transit gateway attachments across multiple accounts in an organization. The AWS CloudFormation create stack set command creates a stack set that can be deployed to member accounts. The permission model parameter set to service managed uses AWS organization's integration for cross-account deployment without manual role setup. The fifth command deploys the stack set to specific organizational units. The AWS CloudFormation create stack instances command with deployment targets specifying organizational unit IDs deploys the attachment template to all accounts in those OUs. Transit Gateway bandwidth and limits. Understanding transit gateway bandwidth capabilities and limits is crucial for designing architectures that meet your performance requirements. While transit gateway is highly scalable, there are important limits and considerations to be aware of. The first command retrieves the current transit gateway quotas for your account using the Service Quotas API. The AWS Service Quotas list service quotas command with service code VPC returns all VPC-related quotas including transit gateway limits. Key quotas include the number of transit gateways per region, attachments per transit gateway, route tables per transit gateway, and routes per route table. The second command requests a quota increase if you need to exceed the default limits. The AWS Service Quotas request service quota increase command takes the service code, quota code which identifies the specific limit, and desired value for your requested new limit. AWS reviews these requests and approves them based on your use case. The third command uses CloudWatch to monitor the actual bandwidth utilization of your transit gateway attachments. By comparing bytes in and bytes out metrics against the theoretical maximum of 50 gigabits per second per VPC attachment, you can identify attachments approaching their limits. The command calculates the sum of bytes over a period and you can extrapolate to determine throughput. There are several important bandwidth considerations. Each VPC attachment supports up to 50 gigabits per second burst bandwidth. VPN attachments are limited by the VPN connection throughput, typically 1.25 gigabits per second per tunnel without acceleration. Direct Connect attachment bandwidth depends on your Direct Connect connection capacity. For peering attachments, bandwidth is limited by the lower of the two connected transit gateways and the inter-region network capacity. The fourth command describes transit gateway attachments with their bandwidth information using described transit gateway attachments. While the API does not directly show bandwidth limits, understanding the attachment type tells you the applicable limit. Best practices and architecture pattern summary. As we conclude this deep dive into transit gateway configuration, let me summarize the key best practices and architecture patterns that will help you build robust, scalable, and cost-effective network architectures. For route table design, create separate route tables for different network segments such as production, development, and shared services. Use propagation strategically to automatically populate routes while maintaining isolation where needed. Create static routes for traffic that should follow specific paths such as inspection VPCs or on-premises destinations. Always verify your route table configuration after changes using Search Transit Gateway routes. For high availability, deploy VPC attachments across multiple availability zones by specifying subnets in at least 2 AZs. For VPN connections, enable eCMP and create multiple VPN connections to aggregate bandwidth and provide redundancy. For Direct Connect, use multiple Direct Connect connections preferably from different Direct Connect locations. For security, implement centralized inspection using AWS Network Firewall or third-party appliances in a dedicated inspection VPC. Enable Appliance Mode on inspection VPC attachments to ensure symmetric traffic flow. Use network segmentation with multiple route tables to isolate environments. Enable flow logs for visibility and compliance. For cost optimization, consolidate attachments where possible since each attachment incurs hourly charges. Monitor data processing volumes using CloudWatch metrics. Consider the trade-off between centralized egress, which saves on NAT gateway costs, versus distributed egress, which reduces transit gateway data processing. Remove unused attachments promptly. For operations, use infrastructure as a service as code with CloudFormation or Terraform for all transit gateway resources. Implement tagging standards for cost allocation and resource management. Set up CloudWatch alarms for traffic anomalies and high utilization. Document your architecture including route table associations and propagation relationships. Looking at the diagram, it shows a comprehensive best practices architecture. At the center is the transit gateway. Connected to it are multiple segments. A production segment shows 2 VPCs with their own route table. A development segment shows 2 more VPCs with a separate route table. A shared services segment includes an inspection VPC with AWS Network Firewall and an egress VPC with NAT gateway. A hybrid connectivity segment shows VPN and Direct Connect attachments. A cross-region segment shows a peering attachment to another transit gateway. Each segment has icons indicating the applicable best practices such as multi-AZ deployment, route table isolation, and monitoring. This comprehensive diagram summarizes the architecture patterns we have covered throughout this presentation series. Thank you for your attendance. Please consider subscribing to the channel and liking this video.